So again, no, will not like go deeper with this flexrotational buckling analysis, no, because I sa kadaghan nga like sa kung daghan na kay nga information inyong makuan, mas maayo man na siyang hinay-hinay then kanang sure, no. So daghan kay siya a formula which is I think, no, it is also like nice gyapon may bal-an ninyo like we will discuss, but sa kadaghan nga information if we will include this one which is I believe, no, and I as far as I remember dili siya included, no, sa board exam. No, I don't remember this one, no. I think we have not tackle this one, no, sa una. Siguro so nang wala ko kadumduman eh. So we'll proceed, no, to build up members. So what are these members, no? Built up members, if the cross-sectional properties of a built-up compression member are known, the analysis is the same as for any other compression members parts properly connected. So ang built-up compression member, those members nga gituyo gid siya og himo, like you have the C shape, gihimo siya nimo og rectangle shape. So bali duha ka C, gaana siya, no, ang cross section. So bali duha ka C, imo siyang gi-weld, no, to make built up, no, that is built up members. The NECP 505.6, so ang analysis niya is actually the same for any other compression member, like kung isa lang ka C, no, or you have there W or wide flange, then naa siya plate sa iyahang flange gi-connect, I mean gi-weld, no. So the analysis is the same to get what is required, no, in the problem. The NECP 505.6 or AISCE6 contains many details related to the connection used above, with separate requirements for members composed of two or more rolled shapes and for members composed of plates or a combination of plates and shapes. The design strength of built-up compression member is a function of the slenderness ratio KL over R. No? Hence, the principal axis and the corresponding radii of gyration about this axis must be determined. Okay. We have this built up members. The double angle or rolled shapes is the most common built up shape, no. You already know double angle, no, kanang angle bar nagkuha na akong ballpen, di nagasulat. Okay, have this the angle and another angle, no, to make it double angle. So this is also an example of built up members. Magituyo nimo siya buhat, no, or fabricate, depende sa design, no, according to the result of the design or analysis. Connection must be ensured that the built-up member acts as a unit, no. So the connection, no, this double angle should act as a team, no, or unit. In ECP 505.6.2 or AISCE 6.2 requires that the slenderness of individual component be no greater than 3/4 of the slenderness of the built-up member. So this provision, no, requires that the slenderness daw of the individual, like this Ka over Ri sub I, should not exceed, no, should be less than or equal to, or should be less than or equal to 3/4 of the slenderness ratio of the whole member, the whole connection, no, or built up member. So this A is the spacing of the connectors. The R sub I is the smallest radius of gyration of the component. Ka over Ri sub I, the effective slenderness ratio of the component, and the Kl over R is the maximum slenderness ratio of the built-up member. Like this individual, no, the Ka over Ri is the effective slenderness ratio of the like individual component, no. What is this spacing of connectors? Okay, let's try. We have this modified slenderness ratio. The nominal compressive strength of built-up members are determined according to section 505.3 or to 505.4 or 505.7, subject to modifications of KL over R. In ECP 505.6 or AISC E6 considers two categories of intermediate connectors as follows. So we have this for snug tight bolts, this provision in ECP 505.6 or AISC E6-1. The modified slenderness ratio, no, you have this notation, close and open parenthesis M, no, is equal to the square root of KL over R squared. So this is, I think, this is the original. Yes, original with O, no O here. Plus A over R I squared, where KL over R, O, no with O, is the original unmodified slenderness ratio. For the old specification of the modified slenderness ratio for fully tensioned bolts or welds, no? This one is for snug tight bolts. This one is fully tensioned bolts or welds. The ECP equation 505.6-2, you have here the modified slenderness ratio is equal to the square root of this, no? KLR squared O, no, original slenderness ratio unmodified plus 0.82 alpha squared. Alpha, this is the spacing of the connectors divided by the quantity 1 plus A squared times this ratio A over R I squared. This RIB, it was not specified in here, so I think this is just RI, no? Wala na siyang B. The new specification of modified slenderness ratio depends on the value of A over Ri. Ri is the smallest radius of gyration of the component, the whole built-up member. Okay. When A over Ri is less than or equal to 40, the slenderness ratio is not modified. Now use equation AISC E6-2A, no? So kung this A over Ry is less than 40, so you use the original unmodified slenderness ratio. But if A over Ri is greater than 40, use equation E6-2B, no? Square root of KL original slenderness ratio squared plus this Ki A over Ri squared, no? You have nanaputay Ki, diba? K sub I. So this K sub I is for lahat nga value, no? Where K sub I is 0.5 for angles back to back, K sub I 0.75 for channels back to back, Ki 0.86 for all other cases na dayon, no? Then A is distance between connectors, R sub I is the minimum radius of gyration of individual component. Note that the column load tables for double angles are based on the use of welds or fully tightened bolts. We have here an example, 4.17 of the book of Sigoi, 2013. The column shown in figure 4.19 is fabricated by welding a 8-inch by 4-inch cover plate to the flange of a W18 by 65 steel with FY50 KSI is used for both components. Effective length is 15 feet with respect to both axes. Assume that the components are connected in such a way that the number is fully effective and compute the strength based on flexural buckling. First is you have to determine the centroid of both of the whole built up member of the whole component, no? Centroid of this plate, this is the plate known as a flange, and this is W18 by 65. So the plate has this area, no? Cross-sectional area, so this 3/8 inch times 4 inches. And this wide flange is actually from the table, no? AASC manual. Kung inyong tanawin dito, you have there the area of the wide flange. And this Y, this is the distance of the, this is the centroid. This 3/8 inch is actually the thickness of the plate. Half of that is the centroid of the plate. Diba? Okay, let me have the calculator.